And I'm basically honored by the invitation and surrounded by this crowd. Many of my scientific heroes are sitting in the audience. So I'm really proud to be here and honored to be. So I'm going to just touch about, I see this as a completely, I don't want this for me. It's not a conference where I come and tell you what I did and I solve and I know. I want to tell you what we did and we don't understand why it's working. And it might relate to other topics. So I'm going to begin by mentioning a few facts about dictionary learning and other things. Very briefly, we can discuss more about that. And then just go into something related, but it's something that we don't really understand what's going on. And I think that's the most fun to talk about. So it's going to be about 3 snippets. The first is going to be dictionary learning. I'm going to try to tell you that you can look at dictionary learning from the point of view of deep learning. And this relates to work that Jan did, and we continue, and it might come later in the talk. And I'm on everything what I'm going to say, my goal is just to basically discuss it later on. Again, instead of a conference, you come for your 20 minutes and you leave. I think the most important part here is the discussion. So please also feel free to interrupt me at any moment. And together for multimodal task learning, I'm going to briefly mention when we consider the data as the features. And that's something that we haven't discussed, and I'm not saying that this is biologically relevant, but it's an interesting concept. And then I'm going to talk, and that's a part that we've been working recently, and it's working too good to be true. And we don't understand really what's going on. We understand it a little bit. And that's why I wanted to present this to this extremely smart audience. And we haven't really published. We have an archive paper, but not much more about that. And it's related to invariance, but we call it helping the data. Since deep structure, I just want to provoke that. And then my third snippet is I want to open the forum to discussions that might happen after the break. So what is dictionary learning? That was mentioned at the end, and it has been around for about 10 years, so I don't want to discuss too much about it. But the basic idea is that you have data, and the data here is represented as columns, and you want to learn a dictionary in such a fashion that every point in your data is a linear combination of elements in this dictionary, and just a few of them. And so that's represented by sparsity. So this is nothing else than matrix factorization, but with a new name. I mean, we know in science that we change names to things every 10 years. So agencies basically believe we're doing something new. And Jan will be the first to say that what was deep learning? It used to be called neural networks. Machine learning used to be called artificial intelligence. But now we have new names. And this is matrix factorization. But the fact that they get new names is because, to be fair, we give them a completely different angle sometimes. And this is not new to anybody that has done Fourier analysis. And it's certainly not new that anybody that has a cell phone in their pocket, because you know what's the #1 use of cell phones? Call, which doesn't work. And then the #2 use is taking pictures, not gaming. It's taking pictures. And you take pictures in your cell phone thanks to this, because thanks to JPEG. And JPEG is a sparse representation on a well-known dictionary, which is the DCT, has a fundamental mathematical basis. It's related to the Karhunen-Loew for Markov signal, so it's really cool basis. Dictionary learning says, okay, those are great bases. Let's see if we can learn a basis that adapts to the data, and the basic formulation is in here. That basis says, okay, every data point has to have a good approximation with your matrix, with your D, and that's a good approximation, and I'm running out of battery. Ben, you have yours, mine is running out. No, battery for this. Sorry, just getting tired on Saturday morning. So I'm going to switch this for 1 second. And, let's see if this is better. And yeah, thank you, Ben. So you're going to try to make sure that you approximate your data. And I'm going to talk in about 2 slides that you can change this metric to say maybe you need to approximate your labels. Maybe you need to approximate something else. But there is a fitting term, fit to something. And then this is a sparsity term. In general, it's the L0 pseudo metric. You count, but you cannot solve for that. So you do all the beautiful L1 type of stuff and nuclear norm that will come back in this lecture. So this is the general formulation. You optimize both for D and A. This is a non-convex problem. If you fix D, it's convex, as Ben was mentioning, once you replace by the L1. If you fix A, it's convex again, but together it's not convex. But as was mentioned in one of the last slides, there is beautiful theory coming out explaining when this actually gives you a global optima. But this is the basic idea of dictionary learning, a fitting term and a sparsity term. You learn dictionaries. I'm not going to use any name to call them because that was a tremendous discussion yesterday. They look to whatever you think they should look like. That's very common. Most of different algorithms get something that looks like this. And this is just for color images. And this has led to a lot of very interesting, in its variations, a lot of very interesting results in image processing and audio processing. It's actually closely related to our very old friend Gaussian mixture models. So you can clearly make the connection of this with Gaussian mixture models, which instead of having sparsity, you have structure sparsity. So we are reinventing Gaussian mixture models. So we're reinventing a lot of things. And I always tell my students, and I want to tell my teachers in the audience, that Jacob Ziff, the one behind the Ziff-Lemper compression, once told that research is nothing else than research. So we just came back to Gaussian mixture models, and that's great. So this is dictionary learning. Again, it has been very, very successful, and it might be a bit jealous of deep learning in the sense that it was the state of the art. It was a component of state of the art for image classification until some people decided to run zillions of computers on zillion square images and beat it with some techniques that I should not mention. But I will mention next. So the basic idea is that this formulation, although it's non-convex, it turns out that you can optimize it with an architecture that comes from deep learning, that relates from deep learning. So the way this is optimized, once again, is you fix D, you optimize for this matrix, you fix the matrix, you optimize for D. So it's alternate optimization. When you fix D and you optimize for the matrix, you open the last 10 years of convex optimization, and they will tell you that there's great techniques, and they all come down to something very simple. And if somebody tells you something differently, don't believe them. They all come down to a matrix multiplication and a threshold, and you iterate. The matrix multiplication comes from the gradient descent. This formulation, although it's convex, when you put this guy on L1, as Ben showed us, has a corner. If you're trying to round that corner, you don't get sparsity. So you have to keep that corner. Basically, it has a convex, smooth, convex, non-smooth. So you do a gradient descent, and you project into your constraints. Every single algorithm out there does that. And they call it by fancy names. And some do it better than others, but they all do that. Matrix multiplication, threshold. And if you iterate matrix multiplication and threshold, you start thinking, if you are old enough, you say, oh, that's what we were doing in the 60s. That's called neural networks. And that's my interpretation of a fantastic paper that Jan had, and that one of my students, Pablo Sprechman, that is moving to Jan's group in a few months, continue. And you can actually then show that you can build a deep learning or neural network to optimize for this. And here comes the first message of the talk. The big difference with everything else that you hear about neural nets and deep learning for this particular case, there are two major differences. One, I know exactly the architecture because the great results in convex optimization told me the architecture. So the architecture is very, very stable from those results. And that's great. So I have one big unknown out of the window. The second is to optimize for this network. I already know an outstanding initial condition that, following the discussion from yesterday, we could call it the result of evolution. The initial condition is what optimization people tell me, that my linear should be the gradient, the matrix that comes from gradient descent, and the nonlinearity should be the threshold that the theory tells me. So I have an architecture and an initial condition that I have books telling me that already does a great job. All what I have to do is basically make it better. And that's a very important difference, and maybe one day will give us an insight into other deep architectures. And the interesting part is that you can do sparse coding, you can do robust PCA, you can do PCA, you can do SVD, you can do all these things that we know about them just by plugging into a neural network, and you see at the end, basically the SVD decomposition of your signal. And it's formally provable that you get that if you just follow the literature on optimization. So that's one interesting concept that I wanted to mention about deep learning. As I mentioned before, and you can take these same architectures and you can change this and say, I don't want to learn a dictionary to reconstruct, I want to learn a dictionary to classify, for example. And you can do that, and you can modify these architectures. You're going to do that, and then basically you can get a dictionary learning implemented by a network that does image classification in the sense that comes the input, and then the output is the class without any SVM or any classifier at the end. It's really the output is what happens. And these are just some examples. This is your query. These are results. And you can actually go a step forward and say, I want to create a network, and I want to learn a dictionary that will take my signal and my image and map it to a very efficient representation for classification. And one of the claims that many people have in the community is that the only way, in the computer science community, that the only way to deal with zillions and zillions of data points is to have a representation which is binary. And then you can do Hamming type of approaches and entering tables. A lot of people believe that that will be the only way to do it. And you can actually do dictionary learning that will create a map to binary signals. And I'm not saying how you do that, but you do the same type of networks, the same type of optimization I mentioned. And these are just some examples. In this case, it's multimodal. This is the query. You should look at this. And you put this, and then you get as output these labels. Green is what the computer was trained to recognize. And in black is what the computers threw out that it wasn't trained, but it's interesting. And this goes into what people call the one-shot learning, that without really ever seeing something like that, it actually recognizes that there are clouds and things like that. And similar here, there are very interesting words that the system has learned. And the system, in this case, the dictionary was learned to take images or images and text and to map them to binary vectors that are useful for classification with the same type of optimization. So it's a different way of learning a dictionary for a different goal. And there is sparsity, and there is all those concepts again. So everything is just, yeah?
Just to understand, so the idea here is that you specify this optimization problem. You specify a way to solve it, basically, and I'm just going to
I specified your optimization way to solve it, and then we try to build a network that the initial condition is that way. The cables follow your way, the initial conditions follow your weights, and then I let it run, and I get away from your weights.
And then you learn away from there.
Yeah. And I don't know, Jan, if you were planning on going in detail on that, but that's basically the concept. The concept is that you can learn, and then you can do, and I didn't bring it because I was lazy to carry. We have audio source separation running on my iPad at 70 times faster than real time, so we slow it down. We have video VGA rates on a laptop in MATLAB running on real time, because you just learn these networks. Okay, and again, we have the structure and the initial conditions from great optimization results. So this kind of brings a connection to dictionary learning and I think some interesting questions. Let me just, I want to finish the dictionary learning with a couple of concepts. And one is something that was raised yesterday, and there was a discussion about evolution, and I don't understand much about evolution besides taking a internet class with one of our faculty that I recommend to everybody. But for me, the discussion was a lot about basically different timescales, because evolution is not done blind where you close your eyes and you evolve. You learn from the environment and you change. So it's different timescales. And in deep learning, people kind of train and supervise and then adapt to the data. And that's kind of what we were doing with these networks. And that's a concept that dictionary learning has been doing from the very first day, from the very first paper, was training dictionaries on generic data and then adapting to that data. So that's an interesting concept that happens. And the last part, because this is going to be my leitmotif in many of my talks, in my three concepts, there is a lot of supporting theory. And I think that's important, that you try to support all this work by fundamental results. And there is a lot of, and there is more emerging. There is really good theory coming out. You can do dictionary learning constraining your dictionary to be elements of your data. And I want to just briefly just explain that in one slide. So instead of letting the dictionary to learn whatever the dictionary likes to learn, you say, I'm sorry, you have to be part of your data. It's kind of the difference between median filter and average. The median, you're restricted to pick a representative from your data. You cannot go away from your data. And it turns out that if you do that, your dictionary learning becomes convex. So you can formulate that as a fully convex problem. And then when you end up is learning, your dictionary are data elements that with them you represent everybody else. Okay? So this is kind of how democracy basically in theory runs. We have senators and you elect representatives. You are not allowed to take the head of one person, the arms of another, and the legs of another. This is the person, you like it or you leave it. And unfortunately, we cannot leave them all out, so we need to pick a few. And here, you are forced to pick a few to represent everybody else. People in physics and biology love this. They don't like dictionary learning because the dictionaries have no physical meaning for them. In this case, they have physical meaning. They are your data. Okay? So in biology, I mean in cell biology and things, they want to understand genes in, genes out. They don't want to understand linear combination of genes. So that's just I wanted to mention. So this is about dictionary learning, and I say there is fantastic papers out there. And you know, I think one of the most interesting papers by Mikel and Freddie Brookstein that gave a non-convex but very efficient optimization to that, and a lot of theory coming out. So since I say 3 snippets and I wanted to talk about features, so dictionary learning is one way to learn features. Here is another way that is also related to basically helping your data. If we want to do face recognition here, and I'm not saying that this has any connections with how humans do it, but from the engineering perspective, instead of having this to recognize, it would be great to have this. So to eliminate this diversity and to have all the image that enter my system look exactly the same. Then it becomes an object recognition problem, and unfortunately we missed David Lowe's talk, but he was going to say probably, that's a solved problem. If you give me an object and you're asking me if that object is in the scene, sift, and it works pretty well. Okay? So it would be awesome if every chair in the planets go through a system and it looks identical. Okay? And that's kind of what we're going to hear talks in the afternoon about invariant theory. So I'm going to show you in a few slides a way to try to force every chair to look identical. Okay? So you might think that you're computing features. You might think that you're computing invariants. I'm just going to make them look identical. You know, I'm not going to manage, but I'm going to try. And here is an illustration. So if all your data points are here in this perfect vertical line, and all your second-class data points are here, there's nothing for you to do. They're all in a nice line. They're very well separated. Great. That life will be very easy. If your data points are like this, and you're expecting noise after that, you might want to open those two subspaces a bit, so you're a bit more robust to noise. If your data is noisy, in this case around subspaces, and I'm showing here the angles between the subspaces is about quarter pi, and there is some distribution on your data, you would like to transform your data so it opens up and it collapses in the subspace. So you would like, and these are true results of the formulation I'm going to show you next, the angles to be as close as possible to half pi, and the variance to be reduced. So you want to collapse the data that is identical and separate the data that is very different. Very simple concept. So let's try to learn a transform that does that. And again, in my group, we compromise between our desires and what we know how to do, or what we think that we know how to do. So I'm not saying that this is how it should be done, but it's something that we can try to do. So here's what I'm going to do. It's just one formulation, and I'm going to do it in the supervised case, although we have the unsupervised as well, but pedagogically it's simpler. Let's assume we have C classes. Now, let's assume that all your data points are identical, and then you put them as columns of a matrix, and then the rank of that matrix is 1, because they're just copies. So you will love for all that matrix of data from the same class to have rank 1. So that's what we're going to try first. But Ben already told you that you cannot minimize for rank, so we're going to put the nuclear norm. So I'm going to try to learn a transform. Forget about this for a second. I'm going to try to learn a transform that I apply to every data point. I look at that matrix, and it has nuclear norm as small as possible. So I'm trying to collapse everything in one set. That doesn't mean it's going to be one subspace, one line. It's just trying to simplify. And then I put a minus here, and I say, but if you put all the data at once, actually I want your nuclear norm to blow. I want you to be as independent as possible. So we have these two competing terms. We know what the lambda from the theory I'm going to show you in a second, so please do not pay attention to this parameter. We want to collapse and separate. This is a non-convex problem, okay? Because we have these competing terms. So we could solve for each one, but not together. But then we wear our engineering hat, and we are going to solve it anyway.
When there's no subscript, it's the whole one.
Everything. And with subscript is 1. Yeah. So you can show very easily that this is a positive energy. You can actually also show that if you manage to find T such a way that you make those spaces orthogonal, then this is 0. There are other ways that are not very friendly to make this 0, like T equals 0, or T have low rank by itself. So that's why you put constraints. But basically, this formulation, if you manage to get, actually, the T that separates has a global optima. And this doesn't work actually. By the way, the rank doesn't open subspaces, because the rank of this or the rank of this is the same. So this is a case where I want to replace the rank by nuclear norm because of optimization. Here, I put the nuclear norm because the rank doesn't work. Okay? So the rank is not everything. Nuclear norm has a value beyond that. You can do this online as data is coming, and I'm giving this. You can, T doesn't have to have the dimension of the data, can actually compress your data. And we don't know, we know that if you compress, it performs better, but we don't know yet what's basically the compression factor, although we have now some interpretations with the group at Duke putting some information theory in this, and we hope that that will give us. So, as I say, you can do unsupervised, and you can also do transforms that are cluster dependent or class dependent. So let me just show you just visually, without saying, oh, this works great, because it works great. I can show you the tables, but I want to show visually. So once again, we went from the angles that we didn't like to the angles that we like, and that was the artificial example. Then we took faces, and I just want to show them is the results are really, really good, but I want to show you what's happening. First, with the clusters. So you take the state-of-the-art subspace clustering technique. So this is the ground truth, projected into 2 dimensions. Colors depends on subspaces. You then try to do classification. You get pretty lousy results using the best subspace clustering out there. But then you start from that, and you learn a transform, and you progress, you progress, you progress. And this is what you get at the end. The spaces just open, and they just collapse. And this is what happens to basically your nuclear norms. They just really go down. And let me just, this is the nuclear norm per class as it started. This is the nuclear norm as it finished. And we'll just do a gradient descent for this optimization. I don't know how to do better. So hopefully people in the audience will. These are the angles between the subspaces, and very low angles, and they open up. They just open up. And what are they doing to the data? They're doing kind of interesting things like this. You take faces from different angles, and they all get transformed to things that are not recognizable for us, but they are much more uniform among themselves. Oh, by the way, we don't do, once we do this, we do off-the-shelf classification. I don't know how to do better, so I take things off the shelf. I don't invent a new one. I just prepare the data. And here is the same, different angles, and you do this transform, and everything becomes kind of much nicer looking. So we've been working on this for a few months with Sam Q, a postdoc that came from Chelapa's group, and we recently put that into a random forest tree. And I'm not an expert in random forest, and for those that are not familiar, random forest is the technique behind the Microsoft Kinect. So that by itself makes it pretty interesting, I think. And the second thing that is interesting is very good theory showing that asymptotically you basically get what you want. A very thick, long paper that shows that. And the basic idea is that you enter with your data, and then you make, is A boost, you make a very simple question, and you go left or right, you make another question, you go left or right, and at the end you get a distribution of, at every node, what's the probability that you belong to that class. Since you're doing a very simple questions, you do that many, 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 many times. You add some randomness between the trees to train them, and then you run your data through all the trees, you sum the probabilities, and you classify. And what we decided to do is at every node, we decided to learn a transform that will make that decision. Same as before. We are going to assume there are 2 classes. So if there are more, we randomly separate them in 2. Every node just splits 2. And we say, all the ones from class 1 have to go together, minimize, minimize. And when you put together, you have to separate them. So just to illustrate a very simple example, these are, let's say, 3 classes. We decide that these 2 have to go together. You see the angles here. At the end, the classes that went together got a very small angle. The classes that needed to be separated go into half pi. And you can look at, this is the transform matrix as we learned. Here we group them in 2, and we get the same. So it's perfectly collapsing and opening. And then you go through that, and we've been doing a lot of experiments with that. And these are just some of the data sets, and I can bore you with tables. But I'm just going to tell you what's happening here. You pick, these are standard data sets that people use for illustrating the power of random forest. And you say, for example, you go to this data set and the state of the art shows 50 trees. We do it with 1. We get the same result. Just 1 tree, just learning this transform. Once you learn the transform, the testing time is the same, because all what I'm saying is before you make any decision, multiply by this matrix. So it's not very hard. And that's basically the order of all the examples. We basically reduce the order of magnitude of the number of trees by one order of magnitude at least. So it's just a nice curiosity. Besides those small theorems, we don't know, I don't know much more what happened. So let me just conclude. So people have been very active in learning dictionaries with really nice theory. And that I briefly went through that. It's an interesting concept when your data are your features. So, and people have worked on that a lot, and that's why I wanted to illustrate. And if your data becomes your dictionary, as I say, from the point of view of engineering, the problem becomes convex, so which is nice. And the last part was about learning transforms, learning to prepare your data for your preferred algorithm. All this, and also here, it has fundamental theoretical results, which I think are illustrative. Some that we did, and some that we borrow from the optimization community. So I want to thank you, and I'm not going to identify, but one of my colleagues that has the office down the road, we were once at a discussion in Norway, and people were very upset about some presentation, and these colleagues say, if it works, there has to be math behind it. And I strongly believe in that. But I took the liberty, because of where we are, to say it has to be math or biology behind it. And I'm going to just finish by paraphrasing, and Shimon might help me, but there was one of the former presidents of the Weizmann Institute that many years ago he said, we only have to teach 3 languages: English, biology, and math. The rest is unnecessary in an undergraduate degree. And I remember him saying languages: English, biology, and math. And I think that's very important. And not everybody is doing math, but at least we should be aware that some people are doing it, and some people are doing great biology. Okay? Thank you. Yes.
So in your subspace learning work, which sounds very interesting, it's somehow related to feature learning discriminants.
Oh yes.
Could you?
We had to do that comparison. Okay, and so it performs worse. But why? Linear discriminant analysis has exactly the same concept, but it's assuming Gaussianity of your data.
Right.
And here we're assuming that it belongs in a union of subspaces. So it's my prior of the geometry of my data is different. And that's basically the concept. If you think your data is Gaussian, LDA, and we know that the LDA is great when the data fits the model. So here I'm doing an LDA for a subspace. Subspace, then I have to, looking at covariances is not really, subspaces is better to look at rank and nuclear norms. But this is an LDA, it's an LDA for subspaces. Yeah. And then I don't have to tell you that LDA doesn't work for these data sets because they're not Gaussian distributions. So, but this works because they are more close to subspaces. Yeah, but that's, thanks for the point. I think it's an important clarification.
With the, using the data as exemplars, I guess the main difference is that you do, I've also run those kind of things on patches. You get surprisingly images out that look like a core wave or something. And, but you end up needing sometimes more of those patches, which is,
No, but I want to tell you something, but maybe because this is a dictionary learn. I guess those that know me, so dictionary learning is nothing else than a different metric for vector quantization.
Right.
Okay? So you have all your data, and you want to represent with a few things, but with a fundamental difference. In vector quantization, you're allowed to pick only one, L2, and you're not allowed to merge. Here, you change your metric, and you're allowed to mix. And when I'm picking the exemplars, I'm doing vector quantization, but I'm forcing you. So I'm limiting your space. So I'm forcing you to pick those. So it's not surprising that you will need more, because I'm giving you less freedom. And if you let's say if you take if I give you a cosine and I force you to pick any other cosine but that one, you're going to need many. But if I allow you to pick that one, so yeah.
I guess the point I was trying to get to is, what happens if you feed those in as starting points?
Everybody does that. Oh, sorry. You know, when you read those papers, nobody tells you how you initialize. Everybody initializes with the data. Either with the data or with things that we know that work great, DCT, wavelets. But those are, and most of us initialize with DCT plus wavelets plus the data, because you're overcomplete. So you just take things that you know that work great. And then your only way is to do better, because you started from something that is great.